Alright, so the idea now is to go back to this equation, and we'll convert it into a family of equations by introducing a small parameter epsilon, which could take a range of values, but so let's just see how that works. So let's define a small parameter epsilon, in terms of which we'll rewrite the equation as x square plus 2 epsilon x minus 1 equals 0. So if epsilon is 0.01, 2 times epsilon is 0.02, and we get back our original equation. Okay, so as before, this is a second order equation, so the roots of the equation are x equals minus 2 epsilon, there's a plus root and a minus root, and 4 epsilon square plus 4 divided by 2. So we've just written both the roots together, x1 comma 2. And we can simplify this by getting rid of the common factor of 2. So let's just write it in a form minus epsilon plus minus 1 plus epsilon square, the square root, and for the square root, let's just write half. Alright, so these are the exact solutions of this quadratic equation. Now in order to see how, or the basic sort of motivation behind how perturbation theory works, what we'll now do is we'll sort of not look at the exact solutions for x, but we'll approximate x in the form of a series expansion in powers of epsilon, which means in integer powers of epsilon. So right now we see that we have an epsilon to the power of 1, but then there's a factor 1 plus epsilon square, which is under a square root. So if we can express the roots x 1 comma 2 in powers of epsilon, that will give us an approximate solution to this quadratic equation, and that will enable us to see how perturbation theory comes into picture. So so let's look at that. Now, if you're familiar with power series representation or Taylor series expansions of functions, then that's basically what we'll be using here. But if not, we'll be doing a series of videos covering those topics as well. So for now, let's just state that say you have a function 1 plus y to the power of n, where n could be any integer, for instance. You can, or even it works even in case of fractional powers. We can expand this in the form of a power series in powers of y, and it reads 1 plus ny plus n minus 1 y square over 2 factorial plus n minus 1 n minus 2 divided by 3 factorial y cube, and so on. So there's an infinite number of terms, and if we sum up the infinite series, the idea is that this series converges to the function at the particular value y we are evaluating within the circle of convergence. So this works for all n could be an integer, it could be a rational number. So now let's use this expansion, and it's sometimes also called binomial expansion, because we have sort of two terms, 1 and y, and that we're expanding. Okay. So what if we apply this binomial expansion to the square root term that we have here? Okay. So what do we get? We have 1 plus epsilon square to the power of half. So in this case, n is half, and instead of y we have an epsilon square. So the expansion will be 1 plus epsilon square divided by 2, and then you have a half. Half minus 1 is minus half divided by 2, so that will give us a factor of 8, epsilon 4, and so on, higher order terms. Now this expansion is valid, or rather this series converges to the value of the function on the left hand side is 1 plus epsilon squared to the power of half within a certain radius of convergence, which in this case happens to be 1, which means we can justify this expansion as long as modulus of epsilon, or in this case modulus or epsilon is less than 1. And that sort of characterizes the smallness of the parameter within which we can approximate the square root in terms of a power series representation of this form. But we'll talk more about these in another video. Okay, so let's sort of, so this gives us an approximation to the square root. Now, how does that help? So now we can go back and look at the equations that we have, or for the roots that we have for x, and express them in form of a power series representation in terms of integer powers of epsilon. So let's do that. Let's write it here. So the first root x1 will be, so you have factor 1 plus epsilon square, so all these terms added, and typically we write these series in increasing powers of epsilon. So so we have a 1, then we have a minus epsilon, and then we have epsilon squared by 2 minus epsilon 4 by 8. And the reason we are sort of not writing or writing dot dots for higher order terms is because, let's say for this particular equation, epsilon is 0.01. So if you raise 0.01 to the power of 4 or 6 or 8, it becomes very, very small. So for now, we can still just ignore those terms. The second root will be, it has a minus in front of the expansion, so it will be minus 1 minus epsilon squared by 2 plus epsilon 4 by 8, and so on and so forth. Okay, so these are approximate expansions or approximate representations of the roots of the quadratic equation. But the interesting thing is that these are in integer powers of epsilon, and that makes it easier to work with them. So let's see how this helps. If epsilon is 0, all these terms vanish, and we get the roots x1, x2 is plus and minus 1. And that's very close to the approximate roots of this equation, because if you remember the exact numbers for this, for epsilon equal 0.01, are the roots are 0.99 and minus 1.01. And to a leading order approximation, which is that is what we mean when we say a zeroth order approximation, is when we drop all terms containing epsilon or set epsilon equal to 0, we get the roots plus minus 1, which offers the zeroth order approximation to our solutions. All right. Now what happens if epsilon is not 0 but is 0.01? Then we'll see that these two factors combine to give us 1 minus 0.01, which is 0.99. So this happens when epsilon is 0.01, and these factors combine to give us minus 1.01. And in fact, these are very, very close to the exact solutions for the quadratic equation in case epsilon is 0.01. So you see that for a very small number, 0.01, even the leading order approximation, like retaining just the first term in the power series expansion, which is epsilon to the power of 1, already gives us a very good approximation to the solution. So this is basically where we sort of step into perturbation theory now. The idea behind perturbation theory or perturbative expansions is, given a more complicated equation, let's say you had an equation x to the power of 20 instead of x to the power of 2 plus 0.02x minus 1 equals 0, then we cannot write down a closed form solution in this form. So what do we do then? What we'll do is we'll assume a solution. We'll assume that a solution exists in the form of a power series expansion in powers of epsilon. So first we have to identify a small parameter epsilon, then assume that a solution exists as a power series expansion in powers of epsilon. Take that as your ansatz or assumption, put it back into the equation, and then systematically solve for the coefficients that appear in that series representation. In other words, let's get rid of this. The basic idea is to look for a solution x, which is, let's say, C0 plus C1 sum epsilon plus C2 epsilon square, and so on. Assume that this is the solution for your equation, put it back into the equation, and then the idea is to solve for these coefficients systematically in a process that we'll now see in the next video. So see you there.